Hello, everyone. My name is Stephen Eliya, and I'm joined today by my group mates, Peter, Carolyn, and Timothy, and we are Styrogrown, a styrofoam packaging alternative. So the initial problem that we came across was that styrofoam is such a popular packaging product around the world. However, there's a plethora of negative environmental consequences that the material has. So we decided to look at different biomaterials as an alternative to styrofoam. However, we came across several different production issues for these biomaterials and found that they're a little too expensive to be feasible for mass producing. We also came across that some of these alternatives were not shock absorbent enough or did not provide ample protection. So going further into our motivation, we originally were inspired by the MAPS project from last year's senior design, which focused solely on mycelium-based packaging, which is the material found in mushrooms. And they use Ecovative's MycoComposite material. So we wanted to make an improved model to this model. And our main initiative was the environment. We wanted to help the environment and the styrofoam problem. So we also wanted to specifically choose ceramic application because of the fragility of ceramics and the fact that it's naturally very fragile. So our logic was that if we could protect those materials, then we could predict that we would protect less delicate items. The expected impacts of our project were to provide a viable packaging alternative for delicate items that is easy to produce and 100% biodegradable. We also wanted to ensure cost-efficient solutions that are easily adaptable from styrofoam as an alternative for different consumers. We want to develop a mass production process and establish a framework to continue this work into the future.
So when it comes to existing methods or really packaging options for ceramics on the market, there's obviously a few out there, but with all these options, there's at least one key issue with them. Either that they're not environmentally friendly, such as in the case of styrofoam packing peanuts and bubble wrap, or they're too expensive and too difficult to make, like geometry paper and molded fiber, making all these infeasible. So diving into the materials of our project a bit, we followed last year's MAPS group suggestion and analyzed the composition of MycoComposite against styrofoam as well as rice hulls and corn-based packaging. MycoComposite at its core consists of hemp herds, flour, and water. Hemp herds were selected due to being sturdy and holding structure even under pressure. Now water, when combined with flour, will actually hydrate the flour particles and actually create a biodegradable binding agent. And when combined with hemp herds, will then form that biodegradable solid material. Corn-based packaging is similar, consisting of corn and water. Corn was selected due to its quick ability to decompose, and when combined with water, forms cornstarch, a sticky starch. When baked, this will also give a solid biodegradable material. Continuing with materials, our rice hull-based packaging consists mainly of rice hulls, flour, and water. And similar to the hemp herds, rice hulls are very sturdy and hold its structure under pressure. And again, similar with MycoComposite, flour and water combined act as a binding agent, and when combined with the rice hulls, form a biodegradable granola-like solid material. All these materials are readily available and can obviously decompose very quickly, making wide-scale production feasible and possible. So kind of diving into making the alternatives a bit, in general, these are the steps that we use to create each one. But at its core, it would involve mixing specified amounts of, let's just say, our hemp herds, corn, and rice hulls with water, and in the case of MycoComposite and the rice hull alternative, flour as well, letting it eventually sit, and then also baking it at specified temperature for a specified amount of time. So getting into the functionality of our final product, it needs to be able to provide barrier protection for ceramic items, has to have comparable weight and cost of styrofoam as well as other packaging options out there, has to be easy and inexpensive to mass produce, and must pass all tests, laboratory and application.
To compare the materials, we ranked them on 3 different categories: durability, ease of production, and risks. And the MycoComposite was the leader in the durability, and the rice hulls was the leader in ease of production and risks. So we decided that we would alter the composition of the rice hulls to improve upon its durability. Some limitations we ran into is that the GIY kit is difficult to use and is a very long process and could grow mold easily. Also, the rice hulls in MycoComposite are difficult to work with and carve because the rice hulls are brittle and the MycoComposite is very dense. Like I said before, mold growth with all of the biomaterials has been an issue since they are biomaterials. And our corn product was actually eliminated before we could get to any testing due to its ease of growing mold. Some risks we ran into are mold growth, it being non-functional for its application, not price comparable, and not time efficient in production, and the manufacturing process would take time to set up. Technology components that we had for creating alternatives was a blender, oven, microwave, and pans. Testing, we used mugs, cars, and a breaking point machine. And then for mass production, we'd use mixers, molds and casts, and an industrial oven. So a general plan for mass production would be to use the industrial mixers first to combine the flour with the biomaterial, use a mold to create a form for the packaging, use casts for the exact indentation of the item, and then use these industrial ovens to bake the packaging materials. And the total production time would decrease since we're no longer having a manual production of mixing and measuring. We would be replacing that with an automated process.
So getting into the testing, in the laboratory, we use the 3-point breaking point instrument, which basically measures the break point of each product. So we tested styrofoam as a baseline, and then we compared it with mycelium and rice hulls. With our new recipe, our altered recipe for the rice hulls, we predict that it will have a much higher break point due to its stronger composition. And we also did some testing with heat and found that putting the rice hulls in high heat for a longer period of time will cause the material to harden, thus creating a more rigid material. So for our application testing, we did 3 main tests, 2 of which we did multiple times. We did drop testing from 3 different heights, and we did that on the MycoComposite and the rice hulls for comparison. We also drove a package with a mug inside of it with the rice hulls and mycelium from my house down in Vineland, New Jersey up to Rutgers. And we also shipped a package to simulate the real life situation from Rutgers to my house. And on the left, you can see the first 2 pictures was before shipment. You can see that it's not broken. On the right, you can see that it did break. However, it still provided the barrier protection needed to make sure that the mug was safe. So for the future of Styrogrown, we would like to see the following. We would like to see that the applications are expanded beyond just ceramics, for example, glassware, and just easier products in general to ship that won't be as breakable. We would also like to see a more efficient process made of making packaging alternatives. And included in that is finding an innovative way to use corn in packaging where it won't grow mold as easily. And we also would like to determine optimal materials for a multidisciplinary use for packaging solution. So in conclusion, through testing and rigorous analysis of biomaterials, we are confident that we have developed a packaging alternative for ceramics specifically that is 100% biodegradable, fully functional, and environmentally friendly. And in the future, we aim for our work to be continued and improved upon in the applications, testing, and production process. Thank you. A special thanks to Dr. Jafari, Yi, and our guest judges. We would like to open the floor to any questions.